Hi, everybody. Last time in our carbohydrate lecture, we talked briefly about glycogen and its role as the animal starch. Well, glycogen is so important, we will be devoting the entire lecture to its metabolism. For our learning goals, we will be identifying the machinery that builds and breaks down glycogen in humans. We will also articulate how glycogen homeostasis is achieved at the organ and the enzymatic levels. And if we're talking about homeostasis, we have to talk about dyshomeostasis. What happens when we break down glycogen's machinery? How will that impact metabolic pathways and the ensuing pathologies? Big surprise, today's molecule of the moment is glycogen itself, and you may not realize that glycogen is actually a type of nanoparticle, believe it or not. Glycogen is stored in the liver as these nanoparticulates, these granules, and they're stored in the liver at a concentration of about 8.1 micromolar. And if we assume a standard liver volume of 1.5 liters, that would mean we have 12.15 micromoles of glycogen particles present. And this here is a graphic of a glycogen particle. We have a protein in the core that serves as like a glycogen anchor. And branching off from it, we have these glucose polymers, the glycogen, if you will. And each of these glycogen particles contains about 55K glucose subunits. So let's ask ourselves a hypothetical. If every single glucose monomer were to be hydrolyzed from all glycogens at once, one, what would the final concentration of glucose be in the liver? And two, why would this be very, very, very bad for liver cells, hepatocytes? And what may help you answer that question is that the typical concentration of a healthy cell is around 300 millimolar. So tease that out and we will discuss later on. As the storage form of glucose, glycogen is a very prevalent polymer. It's about 5% of the dry mass of a liver and about 2% of the dry weight in muscle tissue. And compared to amylose and amylopectin, the glucose chains in glycogen are highly, highly branched. There's about one alpha 1,6 linkage occurring every 10 glucose units or so. And I'll remind you that the 1,4 links are the ones responsible for propagating a chain in a starch. And these 1,6 linkages are responsible for the branching, and glycogen has the most of these. The second best, amylopectin, only branches once every 10 to 25 glucoses. And there are two main perks for having glycogen being so heavily branched. The first is improved solubility. Okay? We have improved solubility with glycogen compared to amylose or amylopectin, and this is the reason why. Amylose consists of long, slender, helical polymers, and you can imagine them stacking together like brickwork really nicely. You're going to have hydrogen bonding contacts that will glue these polymers together, and that's going to prompt them to crystallize out of solution pretty easily. And that's good if you want to create a bunch of starch and stick it in the roots for long-term storage, but that's not good for an organism that plans to tap into that starch and use it perhaps overnight while you're not eating. So that's a problem for animals that need to readily tap into their starch pools. If it falls out of solution, our enzymes can't quote unquote reach it. Glycogen particles are going to experience spherical packing, if you will. And these particles aren't going to lay on top of each other like brickwork as easily, and that's going to facilitate their hydration and prevent them from clumping together and becoming inaccessible. So improved solubility is a really important perk here of glycogen. Now, additionally, glycogen is the most efficient way of storage and release. Most efficient and fastest. Heavily branching glycogen is going to decorate these glycogen particles with these so-called non-reducing ends. These are the ends by which glycogen enzymes will build up and break down the glycogen particle. And if you have more of them per particle of glycogen, that means we can chew them up or build them up faster than just a single chain with two reducing ends. The enzymes chiefly responsible for building and breaking the non-reducing ends are glycogen phosphorylase and glycogen synthase. And we will be discussing how these enzymes work coming up next. Let's talk about glycogen synthesis. At the core of every glycogen molecule is a homodimeric enzyme called glycogenin. Glycogenin is designed to polymerize glucose off of the 194th tyrosine residue, and it will be responsible for starting the first chain in glycogen. The monomer, however, of glycogen is not just glucose, but rather uridine diphosphate glucose, UDP glucose for short. Now, you would think that it would be easier to just build the glucose chain using glucose as the monomer, right? Well, biology goes through the effort of sticking on this nucleoside, this blue UDP moiety that I've circled over there, and there's really two perks of doing that. First, UDP is a good leaving group. If we were to envision this reaction proceeding without UDP as the leaving group, what would that look like? We would have, I'll draw another glucose, or at least part of one over here. And we will have our nucleophilic tyrosine attacking C1. And in this SN2 process, what would serve as the leaving group? Well, it would be this OH, leaving as a hydroxide. And this is a famously poor leaving group. So this process is going to be incredibly slow to the point of it being non-viable. And that's because the charge on the OH is localized to one atom. Now, let's compare this to nucleophilic attack of C1 bearing UDP on it. When we break that bond, what's the product of that reaction? It's going to be UDP. And UDP is going to have a lot of resonance. The negative charge on those oxygens can delocalize all throughout there, which is going to stabilize the product of the leaving group, so to speak. This is something I'm going to say time and again throughout the course. Biology is nothing but applied organic chemistry. I will die on that hill. That is why organic chemistry is a prerequisite to this course. Biology had about 4 billion years to teach itself Orgo 1 and Orgo 2, so be prepared. Now, what's the second reason why UDP glucose is such a good monomer for glycogen synthesis? It's going to serve as a metabolic tag that will reserve those glucose units for glycogen. So the rest of the cell will be able to recognize when a glucose is bound to UDP, it's going to leave its hands off of it and say, oh, the destiny of that glucose is for glycogen. It's not meant for me. Only glycogen pertinent enzymes can bind and recognize it. So glycogenin is going to do this about 7 times and form a heptameric primer with alpha 1,4 links. And then once it builds 7 glycogen units end to end, that chain is going to grow outside of its active site. And so thermogenin can get the game started, but it can't take it past the first inning, so to speak. We need a separate enzyme now to act upon these non-reducing ends, 8 and beyond, and tack it on with additional UDP glucoses. And that's where glycogen synthase comes in. This is an enzyme that can build off of the heptameric primer and also any of the non-reducing ends presented on glycogen. And it will proceed building these alpha 1,4 linkages with identical chemistry to the mechanism of glycogenin. Thermogenin and glycogen synthase are all it takes to extend a chain of glucose units. To make them branched, however, we need to use a separate enzyme called glycogen branching enzyme. It's clever, I know. Once glycogen synthase makes a sizable chain, shown over here, glycogen branching enzyme will come along and it will clip one of these alpha 1,4 linkages. And it's going to break that bond and reattach all of this to the 6th hydroxyl of a glucose 4 residues back. So it's going to pick this whole chain up and go 1, 2, 3, 4 and attach it over there. And what's the product of this splicing? We're going to go from a really long chain with 1 non-reducing end to 2 shorter chains with double the amount of non-reducing ends. This will increase the efficiency of glycogen synthase because we've essentially doubled its substrate, the non-reducing ends. This will accelerate the rate at which we can attach glucose UDPs or the rate we can break them off with glycogen digesting machinery. The reverse process of glycogen digestion or glycogen degradation occurs using a different set of enzymes. Glycogen phosphorylase is like the opposite of glycogen synthase. It is going to cleave off the glucose units by the glycogen's non-reducing ends one at a time. And the way it does this is by breaking the glycosidic bond, specifically the one over here, by inserting an inorganic phosphate group. So it's going to stick in the phosphate over there, giving us glucose 1-phosphate and a glycogen chain that is N-1, one glucose unit shorter, said another way. And the mechanism by which it does this, we won't go into. It's frankly not super well understood, but we do know that it contains vitamin B6 as a cofactor that helps activate this inorganic phosphate to help shove it in and break the glycosidic bonds. And vitamin B6 is also known as pyridoxal phosphate. Now, the glycogen phosphorylase enzyme is going to happily munch along, cleaving off glucoses stepwise one by one until it reaches a branch. And we're going to say until it reaches 4 residues from a branch. And the reason why it stops there is mainly because of sterics. So I just drew an abstracted glycogen branch over here. And if we visualize our enzyme as like a little Pac-Man, you can envision how the Pac-Man is very happy to just chomp away at this free noodle. But once it gets over here, closer to the branch, you can see its like nose is going to bump into the branching point. So it's not going to be able to eat beyond, this little nubbin that we get over there. So we will have to use other degrading enzymes to handle these tricky branching points because of sterics. And before I tell you how we work past those branch points, I'll quickly say what happens to those glucose 1-phosphates we just made. Like UDP glucose, G1P is a substrate committed to glycogen-relevant enzymes. It's not useful in other metabolic pathways. Other enzymes don't recognize it. If we're cleaving off glucoses from glycogen, the cell likely wants to use them elsewhere though. So we can recruit another enzyme called phosphoglucomutase, which will convert G1P to G6P. And that G6P is usable throughout the cell. It is a more promiscuous version of phosphoglucose. The mechanism is fairly simple. We begin with a phosphorylated active site serine, and it will transfer its phosphate group to C6, specifically the hydroxyl on C6. And then we will regenerate our single active site serine by giving the phosphate on the C1 hydroxyl back to serine. So we end up again with phosphoserine in the active site, just like how we started, and we mutated G1P to G6P. Hence, it is a phosphoglucomutase. Pivoting back to glycogen degradation, the way we disassemble the branches left over by glycogen phosphorylase is with debranching enzyme, which is also known as alpha-1,6 glucosidase. The enzyme operates in 2 basic steps. Again, remember that glycogen phosphorylase is going to chomp these off one at a time, but it's going to have to stop over here once we get to 4 residues from our branch, because we can't swallow beyond that point. So what debranching enzyme does first is transfer first 3 glucose units from the degrading branch to a new main chain. Illustrated over here, those first 3 glucose units are shown in yellow. And debranching enzyme will take those and move them over there, giving us a longer chain that glycogen phosphorylase can continue munching down on. And all that's left is a single little glucose double, if you will. The second thing debranching enzyme does, stops off the 4th glucose without phosphorylating it. Now, if you remember, we get about 1 branch every 10 glucose units in glycogen. That means when we fully break apart glycogen, we recoup 90% G6P activated glucose molecules, and 10% is going to be quote unquote regular unphosphorylated glucose. We get the 90% from glycogen phosphorylase and this 10% from debranching enzyme. Now, in your opinion, do these glucoses have the same market value? Are they energetically equivalent? And the answer is going to be no. We are going to talk about glycolysis in a couple of lectures, and the first step is going to be phosphorylate the glucose, activate it, get it ready for more reactions. So we need to invest ATP into these 10% leftovers of glucoses to get them to the same level as G6B. To sum up, we have 4 enzymes in total that enact glycogen metabolism. Let's recount them right over here. We have degraders and builders. The degraders are glycogen phosphorylase and debranching enzyme. The builders are glycogen synthase and branching enzyme. So we have a little bit of a problem. We can't have 2 sets of enzymes with exact opposite jobs running loose. All right? We have to prevent a pointless loop. If we have glycogen phosphorylase and glycogen synthase running unregulated in the liver, we are going to be making and breaking glycogen at the same rate. We won't achieve any net storage or net release. So how do we regulate this? Well, at one level, through hormones. When animals are in a fasting state, the pancreas will secrete glucagon, and this will signal to the body that we are out of glucose. The glucose is gone. That's my way of remembering what glucagon does. Epinephrine, which is the fight or flight hormone, that tells our body we're in danger and we need to get our muscles ready for action and to outrun the axe murderer chasing us. Equals danger. Both hunger and life-threatening scenarios are best remedied through a boost of energy. So these two signalers will act on the liver and muscle respectively to activate glycogen phosphorylase. Specifically, and this is where the glycogen lecture becomes a little comical, they will prompt the phosphorylation of phosphorylase by having it be phosphorylated by phosphorylase kinase. Pause and rewind to get that through. Glucagon and epinephrine are going to uptick phosphorylase kinase, and kinases are enzymes that stick phosphates on other things, and it will phosphorylate these two serines, serine 14 and glycogen phosphorylase. And that will cause a global conformational shift in the protein that makes glycogen phosphorylase more active. And thus, we will accelerate the rate of degradation over the rate of glycogen synthesis. I will also mention that unique to muscle, calcium ions and AMP also activate glycogen phosphorylase. And that is because both of these entities are rapidly accumulating in actively respiring and contracting muscle tissue. Now, if the axe murderer stops chasing us, or if we're able to get to a meal, we don't need to break down our glycogen anymore. So we should shut down glycogen phosphorylase. And the enzyme by which we do that is PP1, protein phosphatase 1. And protein phosphatase dephosphorylates glycogen phosphorylase. The verbiage is unfortunate, I know. And that will revert us to our less active form by stripping the phosphates off of serine 14, thus decelerating the rate of glycogen breakdown relative to glycogen synthesis. Like glycogen phosphorylase, glycogen synthase is also a tightly regulated enzyme, but we're going to regulate it in an inverted manner. Let's begin from the perspective of the fed state. After the body consumes a meal, the pancreas is going to secrete insulin, and that's a hormone that instructs the body at large that we just ate, expect a glucose surge in the bloodstream, soak it up. And part of soaking it up is going to be taking the glucose that we pump into the cells and assembling it into glycogen. So the question becomes, how does insulin drive glycogen synthesis? Well, it does so through two different mechanisms. First, it is going to inactivate an enzyme called glycogen synthase kinase 3. I'll write that out here. And what GSK3 does normally is phosphorylate and inactivate glycogen synthase. Remember, a phosphoryl group doesn't always mean it turns the protein on. Here, it's turning it off. And we don't want to do that after a meal. We want to do glycogen synthesis. So insulin inhibits that kinase from being active, which is going to keep glycogen synthase in an active dephosphorylated state. And that is not all what insulin does. We are going to shut down catabolism and also accelerate anabolism by having insulin activate a contrary enzyme called PP1. That stands for protein phosphatase 1. It's the opposite of GSK3. It is going to actively remove phosphates from any inactivated glycogen synthases, therefore activating them. So this is a very subtle point. Insulin fosters two related but technically different chemistries here. Insulin is going to stop deactivation of glycogen synthesis and promote activation at the same time. These are complementary but not synonymous actions. Glucose 6-phosphate, which is a precursor to glycogen synthesis, is going to have a similar role in promoting activation, but it doesn't shut down GSK3 in the way that insulin does. And of course, we have to discuss what happens in a fasting state now by comparison. How does fasting impact glycogen synthesis? Well, when we are hungry and the glucose is gone, we are going to secrete glucagon. Glucagon needs to instruct the body that it's time to liquidate our glucose banks, the glycogen molecules. Epinephrine, the fight or flight hormone, gets released when an axe-wielding clown starts chasing us. We need glucose to power our muscles to run away. It's going to be hard to get glucose into the bloodstream in either case if we are actively synthesizing glycogen. So both of these messengers are going to deactivate protein phosphatase 1, which is going to help keep glycogen synthase inactivated. Phosphates will come on thanks to an active GSK3, and they will stay on. So glucagon plus epi will stop activation. You may have noticed some trends here between the glycogen synthase regulatory system and the glycogen phosphorylase regulatory system. So insulin causes what's known as net dephosphorylation of the glycogen axis. Insulin activates protein phosphatase 1, the enzyme that activates glycogen synthase by dephosphorylating it, and it's the same PP1 that deactivates glycogen phosphorylase by also dephosphorylating it. This, of course, has the effect of increasing the rates overall of glycogenesis, glycogen synthesis. And it is therefore consistent with being in a fed state. Likewise, glucagon and epinephrine are going to cause net, and take a guess, phosphorylation. Of the same glycogen axis. It is going to inhibit protein phosphatase 1, keep the phosphates on glycogen synthase, shutting it down, and then drive the phosphates onto glycogen phosphorylase, thus activating it. So we have an overall effect of promoting glycogenolysis, or the breakdown. This is, of course, consistent with being in a fasting state. All right, this is complicated, but it ultimately makes sense when you think about it and wrestle with it. We are using a phosphate toggle, if you will, to ensure that glycogen synthesis and glycogen breakdown aren't prioritized or deprioritized simultaneously. Turning one on automatically turns the other off. And the word for this beautiful design of our regulatory systems is called reciprocal control or reciprocal regulation. This reciprocal control ensures that we manage our glucose resources both quickly, adaptively, and efficiently. I know that common parlance suggests that the liver is like this great detoxifier of the body, and that's certainly true, but its role in physiology is really so much more than that. Of its many essential functions in the body, we have to appreciate that it is both a glucose sensor and a glucose reserve. The greatest glycogen repository in the body is actually liver glycogen. But the liver is, I like to call it selfless. And why do I say that? Liver cells do not use this glucose for its own needs, because evolution has taught us that the rest of the body might need it at the drop of a hat. And the way the liver ensures that it is generous with its glucose is through the enzyme glucose 6-phosphatase. As the name suggests, it is going to strip the phosphate off of the 6 position in G6P, which is the ultimate end product of glycogen breakdown. And that's an important enzyme for the liver because G6P is cell impermeable. Only when we rip that phosphate off can the glucose be free to exit the liver, go into the bloodstream, and get carried off to the tissues that need it. Now, on the flip side, let's talk about muscle cells. These, in comparison to the liver, are a bit more selfish. Glucose tends to go in and not go out, at least not as glucose. And that's because, in part, muscle tissue doesn't hold on to glucose for very long. Here's a fun fact if you're into exercise science. It takes about 20 minutes of cardio to blow through your muscle glycogen. So if you're doing cardio for weight loss, it's really imperative that you get your heart rate elevated for more than 20 minutes to actually start entering a deficit. And 20 minutes isn't that long of a time frame. I mean, maybe it feels that way if you're sprinting, but on the grand scheme of things, it's really not that long. And therefore, the muscle needs to rely upon the liver for backup sugar. And therefore, it is going to be selfish and it's going to, by design, lack this glucose 6 phosphatase enzyme. This ensures that while the muscle is working and breaking down its own glycogen into glucose, it doesn't accidentally bleed it out into the bloodstream and waste its fuel. And this is why I wanted to circle back to this graphic so I could highlight some subtle key distinctions here. Glycogen phosphorylase exists in both muscle and liver tissues, but it exists as different forms called isozymes. Now, what is an isozyme? It's going to be an enzyme that has a common general fold and function, but different allosteric sites, which implies they're going to be regulated by different effectors. Recall that the liver's job is to be a glucose sensor or a glucose guardian angel. If there is plenty of glucose going around, it would not be necessary, if not be harmful, if the liver contributed to the blood glucose levels already. So liver phosphorylase will have an additional allosteric site that's going to make it very prone to dephosphorylation when glucose binds it. And that is unique to the liver isozyme. Muscle phosphorylase is a different protein, it's a different gene, and it has a slightly different fold, which has additional excitatory sites that bind AMP and calcium. Both of these chemicals get released during muscle contractions. So if we're contracting a lot, we can expect to contract some more, and we're going to need the sugar to power that. Hence, activate phosphorylase, activate glycogen breakdown, give us fuel. And we can also toggle the activities of glycogen metabolism through the receptor chemistry of the organ tissues themselves. Myocytes have epinephrine receptors, but not glucagon receptors. Hepatocytes have glucagon receptors, but they do not possess epinephrine receptors. Yet, both of these signalers converge onto the same cyclic AMP axis. And this is the meme-worthy part of the lecture. The cyclic AMP axis, what it does is activate protein kinase A, which is called pKa for short. That is all caps, different from the acid-base pKa. But what does this kinase do? Well, it is going to phosphorylate the enzyme phosphorylase B kinase. Which activates it. And what does phosphorylase B kinase do? It's going to phosphorylate glycogen phosphorylase, which activates glycogen breakdown. So I'll parrot that back for you in a nice convenient nutshell. Protein kinase A is going to phosphorylate phosphorylase B kinase, and that's going to phosphorylate glycogen phosphorylase. I mean, it can't get any simpler than that, right? I promise it's less confusing than it sounds. You're just going to have to repeat that to yourselves and write it down in your own less messy handwriting. And that is the crux here of what we call endocrine control of the glycogen axis. By having different receptors on muscle tissue and liver tissue, we are going to ensure that stress will only liberate glucose for muscles when we need it, and fasting will only liberate glucose from the liver to the blood when we're hungry. Said another way, this is going to prevent stress from prematurely starving us and it's going to prevent hunger from prematurely weakening us. It's pretty wild that the body figured out a way to have different isozymes that get regulated reciprocally and are gate-kept behind different receptors. Very, very ingenious. We've learned so far that there are several highly regulated enzymes involved in glycogen metabolism. Unfortunately, some people are born with mutated versions of key enzymes that lose all or part of their functionality. This is known as an inborn error of metabolism, and there are several types pertinent to glycogen chemistry. These heritable diseases, also known as glycogen storage diseases, can manifest when just one enzyme in the network fails to work. And the effects of that can ripple out throughout the body with varying severities and prognoses. I mean, the sad fact of the matter is, the more complicated a system is, the more fragile it becomes. So I want to quickly emphasize that I do not expect you to memorize this table of diseases for the tests. I'm not going to ask you what enzyme gets messed up in GSD type 0. But a question that I can and have asked in the past is, explain to me why von Guericke's disease causes liver damage as a symptom. And what you would do is consult the provided table. We would say, oh, type 1A is von Guericke's disease. The enzyme affected is glucose 6-phosphatase. The liver is affected. We learned that from the question prompt. And the symptoms are hepatomegaly, enlarged liver, and kidney failure. But we're going to focus on the liver issues for this question. And you might be wondering, how do I even begin to answer such a complicated question? My recommendation is to break this down into bite-sized pieces. Ask yourself the following guiding questions. Which metabolites do you predict will decrease if we have a mutant form of glucose 6-phosphatase? Likewise, which metabolites do you expect to surge? And of course, you need to know where this is occurring and how those respective metabolite depletions and accumulations would impact hepatocytes, liver cells. And as a bonus, I also want you to be able to explain why skeletal muscle is not affected by patients that have von Gierke's disease. Why don't you cut your teeth on that? And we will circle back to this when we do our case studies in class after this lesson. I'm looking forward to it.